Hello everyone, and welcome to my presentation of the current research interests of mine. So I will start by discussing orbital resonances and chaotic phenomenology in non-Kerr extreme mass ratio inspirals, which I will define. I'm going to discuss black holes and extreme mass ratio inspiral modeling inside astrophysical environments. Then I will move to the astrophysical environments in the ring down states and to the program of black hole spectroscopy and how it is affected by the environments. And finally, how we can help the black hole spectroscopy program to become more robust with non-model tools. Now, this is what we have. We are on the fourth generation of Earth-based detectors, the LIGO, Virgo, and Kagra, and altogether they have found more than 300 binaries, more than 300 mergers. So we have a plethora of detection to do tests of general relativity, and as you can see, they span from some solar masses to hundreds of solar masses. Therefore, we have a lot of different stages that we can probe and understand space-time with the current detections that we have that are around the kilohertz. The gravitational waves emitted are around the kilohertz band. Now, let's see a very, very simple gravitational waveform with respect to time. This is the amplitude is of order of 10 to the minus 21, and we have an initial inspiral stage. The initial inspiral stage comes after the astrophysical capture. It has circularized the orbit somehow, and these two objects accelerate, and as they accelerate in the gravitational field, they emit gravitational waves. The emission of gravitational waves takes out energy from the system. Therefore, the orbit is shrinking, and as the orbit shrinks, the amplitude of the wave increases, up to the point where we reach the merger, where the two event horizons collide, and we have the maximized emission of gravitational waves. And right after that, the new remnant is slightly perturbed, so it vibrates away the final remaining energy in particular vibrational spectra. Let's start, though, from the inspiral stage of asymmetric binaries. And I will go with full asymmetric binaries in a sense that one component of the binary will be huge. This is the primary, as we call it. It's a primary supermassive black holes, and we're talking about millions of solar masses, and a secondary of stellar mass compact object. This binary is called an extreme mass ratio inspiral, or EMRI. These originate in galactic cores. We actually have pictures of supermassive compact objects in the center of galactic of our galaxy and other galaxies. And the mass ratio between the secondary and the primary spans from 10 to the minus 4 to 10 to the minus 7. Now, the gravitational waves that are generated in this extreme scenario is in the frequency range of millihertz, as we see here. So the detectors we currently have, LIGO, Virgo, and Kagra, cannot see anything like this. Nevertheless, these are very rich inspirals in a sense that they are very slow evolvers, and this will give us a lot of rich orbital and waveform phenomenology that we cannot probe with the detectors we have now on Earth. But luckily, we want to learn more about the universe, as always, and a new detector has arrived out of that, which is a space detector, and it's called LISA. LISA is perfectly suited for this kind of binaries because it has its noise curve has a minimum at the millihertz domain. Of course, we're not building a detector just for extreme mass ratio inspirals, but we can actually probe from black hole binaries to even cosmology. So it has a lot of targets. But let's see a little bit of the schematics of the Laser Interferometer Space Antenna. We have 3 spacecrafts that are separated by 2.5 million kilometers. They follow the Earth in a particular trajectory. And this is not theory, people. This has been adopted and funded by the European Space Agency, will be launched on 2035. And for the first time, Greece is trying to play an active role on this LISA consortium. How we do this? First of all, different researchers are contributing to this LISA consortium as much as they can, but we now very recently have created a member group only for Greek scientists called LISA GR. And I encourage anyone that wants to join to let us know, because this is the state of the art of gravitational waves right now. The president of LISA member group is Nikolaos Karnesis, and I am the representative of this member group in the LISA Consortium Council. In fact, I am a project coordinator of a project called Extreme Mass Ratio Inspiral Models in Dark Matter Spikes. I am associated with the fundamental physics and the waveform working groups, the astrophysics working group. I'm a core member in all these groups, and in the LISA collaboration, I'm a mentor of young researchers, and in general, I am working on this topic as much as I can because I find it extremely fascinating. Now, what essentially we are doing is trying to put Greece into the map of the LISA consortium. Now, let's talk about science, and in particular, let's start with resonances and chaos. So, as I said, these EMRIs, they evolve very slow, which means they evolve adiabatically. So at first order, we can consider them as evolving with geodesics until the gravitational wave emission accumulates and they start shrinking adiabatically. So at the geodesic level, we choose some initial orbital elements, semi-lattice rectum inclination and eccentricity, evolve an orbit. We put a surface of section as this one, and we capture the successive intersections. And this forms this nice target here. This target looks very dull and normal. And I have written here that this is integrability. What do I mean by that? I mean that in the spacetime that we evolved the geodesics, the four-dimensional spacetime, of course, something similar to Kerr or exactly Kerr, we have four constants of motion: the energy, the azimuthal angular momentum, the conservation of the Hamiltonian, and Carter constant. So these four constants can separate geodesics, which are initially four coupled differential equations. We can separate them and reduce one order on the revolution. And this is called integrability or separability. But this does not happen in every geodesic system that we have. We may have a spacetime that is non-integrable, meaning that it lacks at least one of the previous constants that I discussed. In this case, we have something called non-integrability or non-separability. Essentially, we cannot separate VR and theta components of the geodesic evolution, and we have to solve them as they are coupled. But by doing so, we get, if we are away from resonances, these curves that look very similar to what we see at integrability. And there's an actual theorem about that. It's called the Kolmogorov-Arnold-Moser theorem, or KAM theorem, that tells us that as we smoothly depart from integrability, so the curves, the KAM curves, would smoothly depart from the invariant curves of an integrable system as long as we're away from resonances. Now, what happens close to resonances? Why it's so important? There is a Poincaré-Birkhoff theorem. The Poincaré-Birkhoff theorem tells us the following. When we are close to a resonance, the KAM curve disintegrates, but it is not completely destroyed. What remains are the periodic stable points that I show here with black dot, and the unstable periodic points, which are open circles. Now, what is the role here? Why instantly I am talking about resonances? Because this resonant point here is not now forming a KM curve, but KM resonant curves form around it in a structure of an island, and this happens in all stable periodic points. So these islands are called resonant islands, and these belong to the resonance of 2/3. This is the observable here, but not in the Poincare map. I'll show you where. Now, just for completeness, these open circles, these unstable circular orbits, are the points where chaotic orbits emanate. So you see the difference between integrability and non-integrability, separability and non-separability. Now let's go directly to a space-time and do some geodesic analysis and evolve an EMRI with some standard techniques of radiation reaction. The line element here is the line element of Kerr, but with this alpha Q deformation put by hand by us. We don't know what we have destroyed here, but definitely there are some pathologies. But for the purposes of this talk and this paper here, and a successive one in 2021, what we do is we intentionally break integrability by putting this alpha Q different than 0, either negative or positive, in order to break the Carter constant. So now we have a non-Kerr EMRI with a perturbed quadrupole moment. Let's evolve some orbits first. Okay, this is a sketch of a Poincare map. It's very nice. We have all these KM curves shown in black with the consecutive intersections, but the most important thing are these red parts. Why? Because if we zoom into this island, we will see its beautiful nested structure. This is, as I said before, the 2/3 island, 2/3 resonant island, and the periodic point is this one. Periodic means that we have an orbit that starts from some point with some initial conditions. It revolves around the primary sometimes, and then it goes back to its initial point and does the same thing over and over again. This is called the resonance, okay? But the beautiful thing that we need to capture here, and we need to remember here, not forget, is that not only at the central point we have a resonance, but this island is called a resonant island. So the resonance is kept for all geodesics inside the width, inside this big volume of the island. So the geodesics inside the island share the same rational ratio of radial and polar frequencies. Okay, so this is our observable. We find these frequencies, we plot them, and we see what happens. So finding these frequencies is not hard from the evolution of some successive geodesics and a particular methodology, post-Newtonian methodology, to evolve the EMRI adiabatically. And as it evolves, we see that when it enters the island, a plateau is formed. This plateau is formed exactly at 2/3, 0.666667. And this plateau lasts more or less like the width of the island that we found before. In time, we spend 300 cycles in it, in this resonance, so pure resonance for at least a week and observable by LISA. This should give us something. This should be detectable. So if we go to the gravitational wave part of this orbit and we choose one of the harmonics, we see something beautiful. We see the frequency increasing as time passes, and when we reach this plateau, we have some glitch, as we call it, some cut, some frequency jump. And this happens because we entered the resonance, but we entered, first of all, abruptly, and second of all, stayed for a long time, more time than what was expected to happen in a typical Kerr resonance, which lasts for some hours. So this here is an astrophysical glitch. We call it a gravitational wave glitch. It has an astrophysical origin and should not be discarded as an instrumental one. So data analysts have to beware of these things happening in LISA detections. Now, how to detect a glitch and how to extract knowledge from it, this is an open question and we're working on it as I speak. Now, let's add some astrophysical matter because it's very interesting right now. Actually, it's very interesting in the last decades. Why? Because we know that nothing exists in vacuum, essentially, when we are in a galaxy, for example, or a galactic cluster and so on. We have pictures from the Event Horizon Telescope placing supermassive compact objects at the center of galaxies, which are very wealthy. We have the galactic bulge. Around the bulge, we have the galactic disk of baryonic matter. And even around the galaxy, we have a dark matter halo that keeps everything together and flattens the galactic rotation curve. But what's different here? A lot of people in the literature, in the current state of the art, are using the effects of matter as post-Newtonian additions to the dynamics of the secondary. This is indeed, in some sense, correct, but the metric doesn't understand the change in the dynamics from first principles. So the metric, it's still vacuum, essentially. And what we did in 2022 here in this paper, together with Cardoso and collaborators, is that we used the Einstein cluster formalism to build a spherically symmetric line element with a particular matter profile, the Hernquist dark matter distribution, that has some energy density, rho, and the tangential pressures that we calculate. And this line element now has a mass that depends on r because of the halo that has a scale a naught and a mass m, and this mass function has the mass of the black hole plus the components of the halo, in particular the Hernquist halo. And of course GDT has some form. The form is of Schwarzschild times something very complicated, e to the gamma. Gamma is a very complicated function, but it's an analytic one. So what do we get? We get a black hole with an event horizon at r equals 2m MBH. We have asymptotically we are flat. So we have an asymptotically flat black hole. We have the halo around the black hole that enters the spacetime through the compactness m over a naught, which is a free parameter. And if we want, we can even mimic galaxies with this compactness if we satisfy this inequality. The generalization to different energy density profiles and matter profiles is pretty straightforward. We do exactly the same, but the solutions now are numerical and they're not exact like this one. But we can deal with numerical solutions. We have been doing that for years. Now, what is the role of matter and how can we detect that there's an astrophysical environment around an extreme mass ratio inspiral? Let's take it step by step and say that at the level of the metric, when we perturb it, we have two sectors, the axial and the polar sector. Here there's also matter though. The axial sector is pretty simplified because it doesn't couple to matter. So the equation, the perturbative equation of motion of the fluxes that we calculate is very simple. It looks a lot like the Reggie-Wheeler equation. So this is a fully relativistic treatment of an orbit of a particle, a secondary, that performs circular equatorial orbits around the primary. And this is called the source term that describes all that. We see the effective potential here, and we calculate those fluxes to evolve these EMRIs. And what we see are the solid lines for some different compactnesses. Okay. Now, the higher we are, the larger the compactness, the lower we are, the smaller the compactness. But if we calculate this quantity here, which is 1 minus the flux of energy inside the matter halo over the flux in vacuum, so around the Schwarzschild black hole, we see that this quantity, of course, is not zero. So we deviate from the traditional description of an extreme mass ratio inspiral in vacuum. So matter plays a role. In fact, it gives rise to 500 radians of dephasing if we evolve this circular orbit for a year before it plunges the black hole, the secondary. So it's definitely observable by LISA. But we found something interesting here, which we call it the redshift effect. There's this redshift factor, gamma, 1 minus the compactness, which if we put it like so in the equation of motion that we solved before and resolve them, we see that the dust lines differ from their solid lines by at least 2 to 3 orders of magnitude, meaning that what matter does to the axial sector is a simple, um, besides the dephasing, it's a redshift. We have a redshift effect, but we don't expect this to happen in polar perturbations because they're coupled to matter. Don't ask me about the equations of motion. They are extremely complicated. This is a system of 5 first-order coupled ordinary differential equations, and this C in particular encodes the perturbations that we have imposed, that we have decomposed from the polar sector and the matter sector. The polar sector corresponds to H1, H0, and K, and the matter sector corresponds to W and delta rho. All those are coupled very intricately by this matrix A alpha, right? And this is the source, again, of our secondary, which evolves in a circular equatorial orbit, the simplest ones. What we did here is that we solved the equations, we found the fluxes, we calculated the same quantity as before, and we see that they are even more dominant here. Like it's almost 10 to the 2. So this is a strong emission of polar gravitational waves. But the polar sector, as I said, is coupled to the matter as well. So now if we try to do the same thing as before and do redshift, we will not see the same effect. We see that 10 to the minus 1 remains close to 10 to the minus 1, to 10 to the minus 2, and so on and so forth. So first of all, we have done a test that shows that the polar sector is very important in order for us to understand if there is matter around the EMRI or not. Second, we have used a methodology, the Einstein cluster, that is built to capture matter effects. But does it capture all matter effects through the polar fluxes? We don't know. That's what we are studying within the LISA consortium in the project of EMRI models in dark matter halos. And most importantly, is dynamical friction taken into account by this model? Again, we don't know. There's a big collaboration. We're trying to put things together and understand in which limit all the different kinds of effects that have to do with matter perturbations enter the game of EMRIs in astrophysical environments. Finally, the holy grail, as I call it. Cardoso and the student Pedro Fernandez, they built the first rotating black hole inside an astrophysical environment. Now, I instantly snatched this solution and did the first geodesic analysis. Why? Because here we do not just have a black hole with some matter effects around it added by hand. We have a Kerr black hole that rotates and an astrophysical environment that back reacts to the Kerr black hole. So the line element has spin, has a mass, and has a compactness from the halo. This is a general relativistic solution that can be even rapidly rotating, no instabilities whatsoever, and can be highly compact. Again, no instabilities whatsoever. What do we see when we do a geodesic analysis and we plot a Poincaré map? This was amazing when we first saw it, and it was very recently. We see islands of stability. So we have chaos, we have non-integrability. Somehow, when we put the environment around the black hole in a proper manner, that it back reacts to the metric, and we don't use a vacuum metric plus other parts, then we break integrability or separability. And this definitely needs to be taken into account because we see that most black holes are rotating, and they are rotating rapidly, and astrophysical environments are practically omnipresent. Now let's go to the ring down. And really quickly, let me explain what are quasi-normal modes, which I hope that everyone knows. So at the ring down level, at the final stage of a binary merger, that leaves us with a perturbed remnant. The perturbed remnant leaks out energy. It leaks out energy in accord with this quasi-normal mode spectrum. Now, why it's called quasi-normal mode? Because besides the real part, the normal part that has to do with vibrational frequency, it also has an imaginary part, which is the decay timescale of the perturbations. And these quasi-normal modes are in fact a set of numbers which are differentiated in a discrete set with respect to this n. So for n equals 0, we have the fundamental mode. For n equals 1, we have the overtone here in yellow. For n equals 2, we have second overtone, and so on and so forth. So this is where black hole spectroscopy becomes a thing. Calculate the quasi-normal modes, see if we have any deviations with the modes that we expect from general relativity black holes, like a Kerr black hole, and then understand if these quasi-normal modes, if these black hole spectroscopy techniques that we have used match the predictions that we have. Okay, now let's take this game to astrophysical environments. We go back to the previous metric that I introduced, the exact one, the spherical asymmetric one, and now we do not have a source term, so we put it equal to 0 because there's no secondary particle or EMRI. We solve these equations. These are very nice, beautiful figures, but what I want you to keep is the following. I calculate this quantity, which is the quasi-normal mode for L equals 2, M equals 0, and some overtone, N equals 0, 1, or 2, with the astrophysical environment within this setup of the Einstein cluster, minus the vacuum over the vacuum. What do I find? That this is proportional to minus compactness C, which is M over A naught, plus some higher order terms of the compactness. What is this? Simply put, this is a redshift effect. So not only the axial fluxes of EMRIs, of circular equatorial EMRIs, show this redshift effect, but also axial quasi-normal modes of black holes in astrophysical environments do. So the same exact redshift. And it's not only the Herrenquist profile, it's any profile. We have tried different kinds of profiles, the NFW, the NASTO, the JEFE, and all of them have this axial quasi-normal mode redshift. Now, polar quasi-normal modes are in progress. As you saw the equations before, they are extremely hard, and we are trying to put together the results because we have work in progress right now to understand if isospectrality still persists, because now we will have polar plus matter perturbations. It will not, most probably, but we will see. In any case, there are a lot of questions to ask on the topic of testing general relativity. Now, I'm talking about black holes in astrophysical environments, and sometimes things are very predictable. So we add some small perturbation to the effective potential, which corresponds to the environment that we have used, and we get some resulting perturbed quasi-normal modes that lie very close to the vacuum ones, the Schwarzschild ones. But there are some other cases that this does not hold, and I'll show you how and why. Assume that we add a very small bump, a Poisson-Teller or Gaussian bump in some distance a from the peak of the light ring of the Schwarzschild black hole with L equals 2 from gravitational perturbations. Now, put this in a distance far away. What will form between this tiny bump and this big one is a cavity that traps modes. These trap modes are long-lived and they have very, very small imaginary parts, meaning that their decay timescale is very, very large, and they will be the dominant ones. This means that we have a spectral instability because we add such a tiny perturbation epsilon and we get some new modes that are completely different from the ones of Schwarzschild. Here on the right, you can see that we start with the real part of a Schwarzschild vacuum black hole, and then it starts oscillates and it does a discontinuous jump. This continuous jump is from here to here. Why? Because the fundamental mode is no longer fundamental mode, but the overtone that comes down overtakes the fundamental mode, and it becomes the fundamental one itself. Then we increase the distance A, we have another jump, another overtone takes over, it becomes the fundamental mode, and so on and so forth. Here we have 1, 2, 3 overtakings until we have a huge jump of order 10 to the minus 1. So what did we do? We added a tiny 10 to the minus 6 perturbation. We got a huge 10 to the minus 1 migration in the complex plane. This is spectral instability. So we need to be aware of what kind of environments we add and how we add them to the space-time around the black hole. So here, this is what happens essentially in a movie. We start the original fundamental mode, which is the black one, the Schwarzschild one, and it gets destabilized as this distance increases and different overtones become fundamental modes, the ones that are encircled. Now, this is all very nice, but we have done a lot of calculations. We have calculated over and over and over and over again the spectrum of a black hole with a potential and some bump in distance A. And then we moved to a different distance A and did exactly the same calculation. We moved to another distance A, do exactly the same calculation to see how the spectrum looks. But there is a tool, the pseudospectrum, that can be calculated once, and it will tell you the whole story without doing perturbations on perturbations on perturbations. On the left is a Schwarzschild black hole pseudospectrum. On the right is a Horizon-Nordstrom black hole pseudospectrum. I'm going to talk about the right one because it's clean, and then I'll go back to this one. So we see that the pseudospectrum is essentially a topographic map of spectral migration in the complex plane. It shows you the structure of the green function together with the poles, of course, which poles here are the red dots. The blue dots are noise from the methodology we're using, so the poles are the red dots and the rest is the topographic map of the green function. Now, let's choose a perturbation of order 10 to the minus 20. Very small, right? And this places us, let's say, on this line. This is a pseudospectrum contour line of order of epsilon 10 to the minus 30. Okay, so what does this mean? This means that anything above this contour line, all the overtones that live there can spread out throughout the whole complex plane, as long as they are bounded from this pseudospectral contour line. So they cannot go below this line, but above they can do whatever they want. And usually what they do is that they open up and they hit almost exactly the pseudospectral contour line. Everything else underneath this line is still spectrally stable. But by increasing the perturbation, we get more lower and lower contour lines, so more spectral instability. Now, look what happens here at the paper of Jaramillo, which was the first one that introduced the pseudospectrum to black holes. They have imposed the perturbation, as we did before, on the effective potential in a form of a sinusoid, a cosine with some frequency k. And they choose some frequency k and some amplitude, let's say here 10 to the minus 8 or 10 to the minus 4 with some other frequency. What they see is that these perturbations lie, almost all of them, on this contour line. So what did they prove? They prove that when perturbing the potential, you get some logarithmic branches as the ones that we saw before in the movie, in the end of the movie, right? But if you calculate the pseudospectrum, you hit exactly these logarithmic branches that are formed from these perturbed quasi-normal modes. Therefore, we calculate the pseudospectrum once and we know everything about the spectral stability properties of the black hole itself. Now, let's finalize this discussion by saying that we need, and we are, working on fast EMRI waveforms as fast as we can. A lot of them are under construction, and what we're trying to do is include resonances, Kerr and non-Kerr resonances, include environments, include modifications of general relativity, in order to see how these models will compare with future detections from LISA. And especially we need to be very much aware about non-integrability, because it has a very, very strong, big imprint in the gravitational waveform of extreme mass ratio inspirals. Now, we are also working on black hole spectroscopy, and we are making leaps to understand the dispute of overtones to include nonlinear quasi-normal modes and environmental effects, of course, in order to reinforce this ring-down analysis that we have been performing for many years now. Finally, we are complementing black hole spectroscopy, the black hole spectroscopy program, with non-model tools and other kinds of tools, such as the pseudospectrum, that can reveal information beyond the spectrum in order for the black hole spectroscopy program to become more robust. So, in short, this is what I wanted to talk about. Thank you very much. And if you have any questions to discuss anything regarding this talk, please send me an email. Thank you very much.